All right, so today, can everybody with me, please? So today we're going to do something. This is good review probably because we had almost a week off here. This is nothing different than what we did before break. It's just a slightly different approach to the very same thing, right? Before break, we had talked about graphing absolute value functions and graphing quadratic functions and all that stuff. We talked about graphing transformations of functions, starting with the parent function and then translating it horizontally and vertically, stretching it or compressing it vertically, and possibly flipping it, right? Reflecting it. Well, we're doing the same stuff here. So let's warm up with absolute value functions, and then we'll move on to quadratic functions here shortly. So the vertex form of an absolute value function looks exactly like the stuff we were doing last time, right? But instead of thinking about it as two separate translations, we're just going to recognize that, okay, this is a vertex form of a V-shaped graph, and what are the coordinates of the vertex? Well, so on the parent graph, it would be. But if we're going to write this vertex form, that's H and K. Yeah. Right. So the coordinates of the vertex are HK, right? H is the X coordinate, K is the Y coordinate of the vertex. And the axis of symmetry would always be that vertical line through the vertex. So it's always just going to be the line X equals H every time. Okay. So A is what we call the vertical dilation factor. And I would encourage you to think about it that way. Don't use this little shortcut. I mean, it works for absolute value functions, but that's it, right? It so happens that the vertical dilation factor A, because an absolute value function is the right leg is aligned with the slope of 1, when I stretch it or compress it by some amount, that works out to be the same thing as the slope of the right side and the opposite of the slope of the left side. True story, but when you try to apply that to quadratics, it's not going to work so well. So we'll still continue to think of it as a vertical dilation factor. In other words, the number that we're going to multiply by the regular parent height, the height of the parent graph, to either make it taller or shorter, okay? So what about this guy here then? The vertex is located where? For this new absolute value function. What are the coordinates of the vertex? -1, -4, right? Everybody see that? Because -1 is the number that's being subtracted from x inside the function, right? Remember that in vertex form, the sign of h is always the opposite of the operation that connects the number to x. So if it's x plus 1, h is -1, right? Okay, and the axis of symmetry then would be what? What's the equation of the line that acts as the axis of symmetry? Come on, everybody. What? X equals -1. There you go. Okay, good. And so we need to graph this thing. Well, the first thing we want to do is we need to locate the vertex where it's supposed to be, right? So we're going to put the vertex down there. Okay. In this case, the value of A is 1. Agreed? So we don't have to do anything to the parent shape. It's the same shape as the parent graph. It's just been relocated. We're done. Give me 1 to 5. How are we doing? Okay. Same stuff we were doing, right? No big deal. Okay, let's try a little tougher one. What about one like this? So this time, first of all, what are the coordinates of the vertex HK? Yeah, 0, 4. Good. So we'll take our graph, our normal graph, and we're going to move it up to its new location right there. Okay. What's the value of A? Good. So that's the vertical dilation factor, right? That's what we're going to multiply by the parent height, the height of the normal parent graph. Now, the height of the normal parent graph could be described in different ways. It depends how far we walk away from the vertex. If we walk 1 to the right from the vertex, well, the parent graph goes up 1. If we walk 2 to the right, we go up 2. Walk 3 to the right, we go up 3. We'll always just pick the most convenient height. What's the most convenient one to multiply by -7? Probably 1, right? Over 1 and up 1. But instead of going over 1 and up 1, we're going to go over 1 and up 1 times -7. Well, what's that?
Down 7.
Down 7. So over 1, down 7 puts us right there. And so now for our new graph, there's our vertex. There's a point we can use. We've got the axis of symmetry here is the line x equals 0, right? So we could take this guy and that acts as what we can reflect all the points over to get free points on the left side of the axis. If I've got a point here, oh, how did I do that? There we go. So if I've got a point here, I can just reflect that over the axis horizontally to get a free point, reflected point on the other side. Right there. And then all I'd have to do is just use those points to create my V-shaped graph. Starting at the vertex, I would just go through that point for the right leg and through that point for the left leg, and I got it. Okay, 1 to 5. No sweat, right? No big deal. Okay, how about this one? Little trickier. What are the coordinates of the vertex, first of all? Okay, good. So what is it again? Negative 1, -1, right? Remember, it's got to be the opposite of that. So -1, -1. So we're gonna locate our vertex there. Okay, what's the value of A? Okay, so I'm going to multiply A by a convenient parent height. Well, what would be a convenient parent height? Over 1 and up 1. 1's not a very convenient height to multiply by the fraction 2/3. What about over 2 and up 2? Thumbs up or down? Is 2 good or bad? I say bad. You can still get a fraction. What about over 3 up 3? Ooh, that's good, right? I'd rather multiply 2/3 by some multiple of 3 so the denominator cancels, right? So let's choose the value over 3 up 3, and let's multiply 3 over 1 times 2/3, and that's going to give us, what, 6 over 3, which is 2. That's convenient, right? So we're going over 3 and up 3 times 2/3, which is 2. So we're going up to there, right? Okay, so now we know we've got a point there and there. We've got our axis of symmetry, so we can just reflect this point over to the other side and get a free point over there. And then all I've got to do is make my V. It's just a little bit squished, isn't it? It's only 2/3 as tall as the normal graph would have been, the parent graph. Okay, give me 1 to 5 on that one. How are we doing? Okay, good. All right, you guys are getting this. This is good. Okay, let's reverse it once. So now I'm giving you a graph, and I want you to write the absolute value function in vertex form. So all we really need are just numbers to plug in for A and H and K. Yes, ma'am?
Did you start the video?
I hope I did.
Yeah, you did.
Oh, okay, yeah, I did. Perfect. Awesome. Thank you for checking, though. Thank you for checking.
I was more concerned about my shoes.
Yeah. So what do we get here for H and K? What do you think?
Is H4 and K is 3?
Close.
Wait, negative.
-4. Yeah, because H and K are just the coordinates of the vertex, right? So we get,
I thought that you needed to be switched over like this, like when you switch over.
okay, that's going to get taken care of when we plug the numbers in, right? Those are the values of H and K. Now we need a value of A. That's a little trickier. Yeah, it's 1/2, isn't it, right? And we can see that because instead of going over 1 and up 1, we're going less than that. That's not very convenient, but it would have been convenient normally to go over 2 and up 2. We're going over 2 and up 1, right? So all we have to do then is set up the equation that uses A, right? It's A times the normal parent height. So 1 times A equals, 2 times A. It's A times the parent height, right? I got that messed up. So 2 times A equals the dilated height, which was only 1, right? So if I solve for A, we just get A equals 1/2, right? Everybody see that, how we get that? We multiply A times the parent height to get the dilated height. So A equals 1/2. If we plug all this stuff in then, 1/2 goes in for A, -4 goes in for H, 3 goes in for K. What do we end up with? F of X equals, yeah, I get 1/2 out front. Shouldn't be any talking. 1/2 out front. X minus -4 turns that into an X plus 4
Wait, you said
inside.
you were talking, but we were answering the question.
Oh, what was it? Oh, were you?
We were saying like 1/2 that we were starting.
Oh, okay. I thought I heard other stuff going on. Sorry. So X plus 4 is inside the absolute values, right? And then outside we get plus 3. And there it is. Okay, good. Good. All right. So now we graduate to quadratic functions. Okay, but it's no harder. It's the same stuff, just a slightly different parent function. So what's vertex form of a quadratic? Oop, that's wrong. Should be quadratic function, not equation.
It's wrong on yours, but it's right on ours.
Okay, that's good. So what is vertex form of a quadratic function? F of X equals, keep going, tell me. A times,
The absolute value.
well, not absolute
Oh,
value.
no, it's not absolute value. Oh my
Quantity X
God. Is it
minus H squared. Good.
plus? Okay.
There you go. Plus K. You got it. That's it, right? Okay, it works the same way, right? H and K are the same number. They mean the same thing. So the vertex in this case is just like before. The vertex is the ordered pair HK, and the axis of symmetry is still just X equals H, just like with an absolute value graph. A is the vertical dilation factor, so it still determines the width and the direction of the parabola. Width is really a bad, let's change that too. If it says width on yours, let's change that. Because really it shouldn't be the width. What should it be? It's the height. And there is a little bit of a difference, right? I know that you can make them the same thing, but what we're really doing is we're stretching or compressing vertically. So it's really the height that we're controlling. And remember, so if A is positive, the parabola is opening up. If it's negative, it's opening down because it's been reflected, right? Vertex form really just shows us the vertex of a quadratic function with respect to or as compared to its parent function, f of x equals x squared, okay? So let's look at an example down here then. We've got this function f of x. What are the coordinates of the vertex of that function? Whoops.
Is it 7 and -5?
Could it be -7 and
-7, -5. Yep. Yeah. That's true.
I was looking at the equation.
Well, okay, but on the equation, remember, h is defined as the number that's being subtracted from x inside the function, always, with any vertex form, okay? And what's the equation of the axis of symmetry then?
Or -7.
X equals -7. Okay, x equals h, which is -7. Okay, so now think about this. If a parabola has a value of a that is negative and it opens down, then the vertex becomes the maximum value of the function, right? The biggest y value, biggest output value. If the parabola opens up, the vertex becomes the minimum y value or output value. So for this one, a is +3, right? So it opens up. So what is the minimum value of this function? Okay, but the minimum value is going to be the output value. So which one is it? -5. Yeah. And that comes from right there. Okay, it's always the y coordinate of the vertex. It's always going to be the maximum or the minimum, depending on which way it opens for a parabola. Okay? And does the graph make sense? Well, yeah, the vertex would have to be at -7, -5. Now, what about the a part? So a is equal to 3. That means we're stretching the parabola by a factor of 3, right? So we're going to take a convenient height of the parabola and multiply it by 3. Well, the most convenient for this one would just be over 1 and up 1 normally, right? Though on the parent graph, we go over 1 and up 1 squared, which is just 1. So we're going over 1 and we're going up 1 times a, which is 3. So up to there. Okay? It's stretched out vertically. And then we'll just reflect that point over the axis of symmetry to get a free point on the other side. Okay? How about this guy? Coordinates of the vertex. Yeah, everybody buy that? -2, 0. Okay, so we can take this graph and move it down to there. Okay. What's the value of a? 1. So I'm done, right? I don't have to stretch this thing at all. That's it. Okay.
I think you're supposed to move it left.
Oh, did I move it the wrong way? Oh, you're right. You're right. Right there. That's where it should be. There we go. Thank you. Okay. Okay, what about that one? So we're using example 10, but we're going to do some other stuff with it here. So given this function, and here, let me put a box around. It's kind of hard to see. There's the function. Okay, so first of all, give the vertex. What's the vertex?
-5, -1.
There you go. -5, -1. So -5, -1 puts us right there. What's the axis of symmetry? Well, it's not. It's an equation, though. X equals -5. Okay. So here's our. Oh, that's kind of inconvenient, huh? There we go. Okay, so there's our axis of symmetry right there. X equals -5. Let's graph this thing. Oops, not there. Huh. Put it the wrong spot, didn't I? It's got to go. Come on, where is that thing? There we go. It's got to go over there, doesn't it? Okay. There's our axis of symmetry. Okay, so what's value of a? -1. So instead of going over 1 and up 1, we're going to go over 1 and down 1. Up 1 times -1. So that puts us So that puts us there, which gives us another point on the other side that's been reflected. And so we end up with something like that, right? Okay, what's the domain? What's the domain of this graph? It's for every parabola, it's all reals, isn't it? What's the range?
-1 to -infinity.
Okay, right idea, but not stated correctly.
-infinity is -1.
There you go. Okay, so the range, -infinity to -1. What do I need with the -1? Brackets. Because -1 is a y value that is included in the graph. Okay, how about this one? What about, we need a new color here, we'll go brown. What's the largest open interval of the domain where the function is increasing? So where is this function increasing? No, it is. What's the rule for increasing? How do we know when a function's increasing? No. Where's the function increasing? How's an ant walking when a function is increasing? Oh, where is it, Deegan? He's going up. He's going up when he's walking in the positive x direction. If he's walking uphill, the function is increasing. So where is that happening? Where is the ant walking uphill from left to right? -infinity, not to -1. We're talking about x values here, right? To -5. Oh, okay. So it's increasing on -infinity up to -1. Brackets or parentheses? Parentheses. Parentheses. Oh, sorry, -5. You're right, -5. -5. We need parentheses, though. How come? How come we need a parenthesis with the -5?
You wrote -1.
I know, but oh, okay. So I get you. Because it's not increasing there, right? It's increasing up until that point, but at x equals -5, it's horizontal, right? That's the transitional point. So it's increasing on that interval. Where is it decreasing? Yeah. So it's decreasing to the right of -5. So -infinity to, or -5 to infinity, again with parentheses though, right? Okay, give me 1 to 5 on that. Does that all make sense? Okay, all right, we're good. And then that's it, okay? How about this one? Throwing you a curveball. So look at this. Man, that's mean, huh? I've given you a quadratic inequality in 2 variables. Okay, but this one, this shouldn't be that big a deal. Think about how we graphed regular linear inequalities. We graphed the boundary line, and then we shaded a half plane, either above or below the boundary line. This time, instead of a boundary line, it's going to be a boundary what? Parabola. Yeah, it's going to be a boundary parabola. Is it going to be dashed or solid, you suppose? Dashed, because there's no equal sign. And then we're going to graph the boundary parabola the same way we've been graphing all this stuff.
Is it also going to be an open point?
Going to be what?
Like when you put a point on a line, it's going to be an open circle?
Hold that thought. Hold that thought. So what are the coordinates of the vertex, first of all? 3, 1. Okay, good. So we know we've got a point at 3, 1. And I'm just going to make it a point for now. But your point is well taken, Gideon. It probably actually should be an open endpoint. But we'll worry about that when we get there. So there's my vertex. What's the value of A? Okay, -2/3. Now you got to pay very close attention to this part. So think about the parent height that would be most convenient. Well, let's write down a couple of different options. So when I'm graphing my parent function from the vertex, I would go over 1 and up on the parent graph of x squared. From the vertex, over 1 and up 1. Okay. Over 2 and up, no, 4. Because I'm going up 2 squared, yeah. So over 2 and up 4, over 3 and up 9, okay. Which of those would be the most convenient height to use? 1, 4, or 9? Are you guys wondering why we went up 9? Okay, that makes sense to everybody? Okay. Okay, so which one would be the most convenient one to multiply by negative 2/3? 9, yeah, right? Because 9 is a multiple of 3. That would make sense. So if I multiply negative 2/3 times 9 over 1, what's that give me? I get negative 18/3, which is just negative 6, right? Everybody see that? So I'm going to go over 3 and up 9 times negative 2/3, which is negative 6. So look at that. Now I'm getting a vertex there. I'm getting a point there. I've got my axis of symmetry. I can go ahead and reflect this point over my axis of symmetry to get a free point on this side. And those are the points I'm going to use to sketch my parabola, which you already told me is going to be dashed. So it's going to look like, kind of like this. Like that, right? There's my parabola. Am I going to shade now above or below my dashed parabola? F of x is less than the parabola. So below, yeah, I'm just going to shade below. So it ends up looking like then, it's going to be kind of strange. It's going to look like, you get the idea, it's all that, it's like an infinite bullet or something, right? That just goes down, okay? Makes sense? It looks like, if you want a more exact graph, it looks like that. Okay, so what would happen if you graphed a system? What if I added another parabola to that? I had y is less than the one we just graphed, and then I'm also going to have the other parabola, y is greater than or equal to, so solid boundary, x squared minus 4. And if I did that one, it would look like that. Again, just like before, I'd be looking for the overlapping regions, which would be that one little thin section in the middle where they overlap. Okay, make sense? All right, go to it. That's it.